Next, let us talk about the thermal effect. First, we look at the thermal coefficients of gauge factor. This is referring to the gauge factor variations caused by the temperature. We have mentioned previously, strain gauge is very sensitive with the temperature. Temperature can lead to expansions of the sensitive element in the strain gauge, and this lead to expansions of the sensitive element, and the expansions of this sensitive element shall change the cross-sectional area of the element and influence the resistance of the strain gauge. Now the strain gauge resistance change. By computations, there will be strength even though it is not exist. Previously, we also mentioned the gauge factor here is a constant number correlating the changes of resistance with the strength. This is provided under the normal circumstances. Now, in the case of high temperature, the gauge factor should theoretically change due to the changes of the resistance caused by the temperature, and this brings to temperature coefficients for gauge factor. Now let us look at this figure here. We have the sensitive elements of the strain gauge made of two types of alloy. The first one is copper-nickel alloy. Another one is nickel-chromium alloy. For your information, alloy is a material made of two or more metals, or made of a metal and a non-metal. In this case, the sensitive elements of the strain gauge is made of copper and nickel and chromium. These two types of alloy have different response under temperature. The y-axis here represents the gauge factor change with temperature, while the x-axis here represents the temperature. Both lines intersect 0 at 20 degrees Celsius. That means if you are conducting testing under the temperatures of 20 degrees Celsius, no corrections in terms of the gauge factor is required. You may acquire the reading directly from the data logger based on the gauge factor given by the strain gauge. Now, if you are testing the specimen other than 20 degrees Celsius, there will be variations in terms of the gauge factor as given by two different alloys. Taking this nickel-chromium alloy as an example, the line here is going downward. It means that the gauge factor of nickel-chromium alloy decreases as the temperatures increases. If possible, you will need to make some corrections to the gauge factor. Bear in mind that theoretically you can still use the strain gauge under high temperature as long as structurally caused damage does not occur. Only that you need to do some corrections in terms of the gauge factor that you use to compute the strain. However, reaching to a certain stage, structurally caused changes occur. Theoretically, when this happens, the strain gauge cannot be used. This one, it will be exceeding 200 degrees Celsius. Therefore, to be safe, never use strain gauge under the temperature more than 200 degrees Celsius. And if you wish to have the accurate result, test your specimen at 20 degrees Celsius without any corrections to the gauge factor. Next, we talk about the coefficients of linear thermal expansion. First, you need to know what is the meaning of linear thermal expansion. When a material is subjected to temperature, This leads to the changes in terms of dimension. The higher the temperature, the bigger the size, while the lower the temperature, the smaller the size. Now, an unrestricted material, when subjected to change of temperature, the dimensions change uniformly throughout the entire material. This is especially applicable for strain gauge, as it is composed of thin layer of sensitive element. Now, in terms of TML, the coefficients of linear thermal expansions, it will be 10 power of -6 per degree Celsius. Next, we talk about gauge hysteresis. What is hysteresis? It is referring to the phenomena in which the value of physical property lags behind the changes of the effect causing it. What does it mean? That means a delay response of the gauge in terms of the measured value versus the actual strength. That means the response of strain gauge in terms of the measurement is slightly lagging behind the actual situation. And when this occurs, it is known as gauge hysteresis. This gauge hysteresis vary depending on the factor such as the grid configurations, base material, adhesive, and temperature. You can understand this in this figure. This is your strain gauge. The one that actually doing the measurement is the sensitive materials that conduct electricity, which is this foil, and it is placed on the gauge base. Now this gauge base is attached to the test specimen using an adhesive. What you are doing in the testing, it will be applying the force onto the test specimen. The force here leads to the changes in terms of the strength, and this strength shall be transferred to the adhesive and then to the base of the strain gauge and then to the sensitive element. The test specimen will elongate first, followed by the adhesive and then gauge base and then the sensitive element, and then by measuring the change of resistance, we are able to determine the strength happening within the sensitive element, and it is assumed that the strength as measured by this sensitive element is equivalent to the test specimen. This is provided that the gauge hysteresis is overcome. Next, we talk about the thermal hysteresis. This is referring to the hysteresis that occur in the heating or cooling cycle, such that the test material is being heated and cooled in various cycles. However, due to the delay of the readings given by the strain gauge, it might end up the respective cycles of heating and cooling cannot be fully identified. Let's say now your strength is something like this, but because of the hysteresis, if you only manage to acquire the reading here, it might end up to be a constant strength throughout the process. Now, this temperature hysteresis poses an ongoing problem in strength measurements when the temperature change occurs. If this happens, precautions will be required. You will need to remove this hysteresis by applying the heat treatment to stabilize the characteristic of the strain gauge and the adhesive. I believe this is already highly specialized, and your test specimen involve the changes of the temperature. Then you have to be careful with this. This shouldn't be a problem for general application. Next, we talk about gauge zero drift with temperature. This is another effect of the temperature. Now at high temperature, the effect such as the thermal oxidations of sensoring element in the strain gauge can cause the 0 point of the gauge in a non-load stage to gradually drift. What does it mean? You know that metals tends to oxidize. The reactions will be faster under high temperature. Now under high temperature, if the thermal oxidations take place on the sensitive element, that means you are talking about the wire or the foil of the strain gauge, this is going to influence the reading. Even though the strain gauge is not subjected to any load, however, because of this thermal oxidation, there will be readings, and this is known as the zero drift of the strain gauge. And this phenomena is one of the characteristics that determine a strain gauge resistance to heat. Based on the information given by the reference, above 200 degrees Celsius, nickel chromium alloy performs better than the copper nickel alloy. And alloy such as platinum tungsten can be used in 500 degree to 800 degrees Celsius environment. So if you need to test your specimen under high temperature, you might need to consider the alloy that is used to produce the sensitive elements in the strain gauge. Next, we talk about the self-temperature compensated gauges. You know that a change of ambient temperature can cause a variations of strain gauge resistance. These variations is due to the thermal expansions of both strain gauge material and the specimen, and it is affected by the thermal coefficients of resistance of the strain gauge material. Now, these self-temperature compensated gauges are commonly used to minimize the gauge temperature output when bonded to the test specimen, which have specific linear thermal expansion coefficients in specific temperature range. And then we have temperature compensation range. This refers to a temperature range in which the thermal output of self-temperature compensated gauge should be within the given range. That means this is the range which the self-temperature compensated gauge is applicable. Now this compensations is accurate within approximately plus minus 1.8 times 10 power of negative 6 strength per degree Celsius, as represented by the figure here. You know 20 degrees Celsius is the benchmark. The measurement is the most accurate at 20 degrees Celsius. Now the limit is set within these two lines here, plus minus 1.8 times 10 power 6 strength per degree Celsius. The larger the temperature, the bigger the variations. Now as long as the indicated strength given by the strain gauge is within these two lines, it is still considered acceptable, and this is referring to the temperature compensation range. We know that the accuracy is the greatest for strain gauge at 20 degrees Celsius. Under high temperature, there will be variations in terms of the indicated strength versus the actual strength. Now, if you need to measure strength in high temperature, corrections can be made by modifying the gauge factor that you use to compute the strength in the strain gauge. It is so that the strain gauge yields greater accuracy result. Now the question is, how do you correct the strength? You may refer to the curve for apparent strength versus temperature, which is supplied in each package of gauge. In every package, there will be a piece of paper, looks something like this. There is a graph here, and this is a graph that you use to do corrections if you are measuring strength in high temperature. Referring to the graph here, the y-axis it will be the apparent strength, and the x-axis here refers to the temperature. The temperature range from 0 to 150 degrees Celsius. There is one more y-axis here representing the variations of gauge factor with temperature, or temperature coefficients of gauge factor. You have two lines here. The solid line represents the apparent strength. The dotted line represents the gauge factor. Now the gauge factor by default is 2.3 plus minus 1%. This is applicable to 20 degrees Celsius. The temperature coefficients of gauge factor is given here, and it is also referring to 20 degrees Celsius. Let's say now you are measuring a specimen under high temperature. You may refer to the curve here. Based on the factors here, do some corrections to your results. Personally, I have never dealt with testing of specimen under high temperature. I have never used this before. How it is actually work out, I have no idea at the moment. However, I believe that by referring to the curve here, the value that you obtain from this axis in terms of the variations of gauge factor with temperature, as well as the temperature coefficients of gauge factor. Let's say now we are testing at 100 degrees Celsius. The variations it will be about 1%. I believe that 1% shall be added to this gauge factor and the temperature coefficients of gauge factor. Correct me if I'm wrong. Next, we talk about the operating temperature range. This is referring to the temperature range within which a strain gauge can be used continuously under appropriate conditions. That means it is the applicable temperature range for different types of strain gauge. You may refer to the figure here that shows the temperature output characteristic for different types of alloy. You have copper nickel alloy, and you have nickel chromium alloy. Most strain gauge use copper nickel alloy, while nickel chromium alloy is used in strain gauge series that has a wider operating temperature range. How do we read this figure? The copper nickel alloy range between here, while nickel chromium alloy range from negative 300s to 300s. The applicable range is larger.